Hello everyone. We'll start with the problems on effective pressure. Okay, the problem number one reads like this. A layer of clay 4 meter thick is overlain by sand layer of 5 meter thickness, the top of which is the ground surface. Means what? A layer of clay is there 4 meter thick. Above that you have got 5 meter thick sand, and top of the sand is nothing but ground surface. The clay overlay is an impermeable stratum. Okay, initially means clay is lying above impermeable strata, that is to say initially the water table is at the ground surface, but it is lowered 4 meters by pumping. So you got 5 meters thick sand in that beginning top to the top of the sand itself is the water table. Now it is lowered by 4 meters by pumping. Calculate sigma dashed V, that is vertical effective pressure, at the top and at the base of the clay layer before and after pumping. For sand, E is equal to 0.45, G is this, SR, that is sand after pumping, means degree of saturation for sand after pumping it out, 50%. For clay, White's ratio is 1.0, G is 2.7. This is the data. Now in these kind of problems, what you have to do is first of all you have to draw the sketch of stratification. So there is a 4 meter thick clay, above that is a sand 5 meter thick, and above that it is a open air only, because that is the ground surface. Now there is water right up to the top in the beginning. Then they have said some data has been given like E and G and SR, right? So gamma saturated of sand in this condition, this is gamma W G plus C divided by 1 plus C. Gamma W is 9.81. G, it is given 2.6, right? And assuming that White's ratio will not be changing, right? E is 0.45. So with all this, the gamma saturated of sand will be 20.635 kilonewton per meter cube. Similarly, gamma saturated of clay, the same formula, 9.81, G is given 2.7, and White's ratio is given as E equal to 1. So substituting this and simplifying, we get gamma saturated of clay as 18.15 kilonewton per meter cube, right? Clay is having gamma saturated as 18.15, whereas sand is 20.635. Okay, now after drawing the stratification and then gamma etc, okay, here at the top of clay layer, because they have asked you to calculate sigma dashed V at the top and base of the clay layer before and after. So at the top of the clay layer, before pumping, means there is no water table changing, it is here itself, right? Now sigma V is because of saturated soil, that is total pressure, that is 20.635 gamma multiplied by 5 gamma H. So 103.175 kilopascals is the vertical pressure at this level. Now U, that is pore water pressure, is 9.81 into 5. Obviously, if you insert a piezometer at this level and then held it high like that, because it is a free water, obviously the water will rise up to 5 meters. That is to say, Pore water pressure is 9.81 into 5, that is 49 kilopascals. So hence the effective pressure at this level, sigma dashed V, will be sigma total pressure minus pore water pressure, that will be becoming 54.175 kilopascals. Okay, so this is at the top of the clay layer. Now at the base of the clay layer here, again we'll calculate total pressure. Total pressure will be, because of standing soil, it will be directly 103.175 plus this gamma saturated of the clay multiplied by 4, 18.15 into 4, that gives you 175.775. So if you want total pressure at this level, it will be gamma saturated of this multiplied by H1, gamma saturated of this multiplied by H2. Like that, if you do, you'll be getting the same answer, because 20.635 into 5 plus 18.15 into 4, it's one the same, 175.775 kilopascals. Now you pore water pressure, again you imagine you insert a piezometer here, it will rise up to 9 meters. So 9.81 into 9, 88.3 kilopascals. So sigma dashed V becomes 175.775 minus 88.3. That will be 87.475. So this is at the base, at the top, but only before pumping. Now we'll go with the pumping condition. So it is pumped down by 4 meters, it is said, 1 meter is still left there, right? Now if we want to calculate the pressure at the bottom, here we'll have to have this gamma plus this gamma, right? So let's see what we can do here. That is 5 meters fine, 1 meter is that's right. Now look at this, gamma B, bulk unit weight of sand, that is here. It is not dry, because it is given, degree of saturation is given as 50%. So gamma sand of SR 50% is equal to G gamma W divided by 1 plus W divided by 1 plus E. This is W, right? Water content, but how the water content is calculated? Because S into E equal to W into G, we know this formula from which water content can be calculated, because it's given E is 0.45, degree of saturation is mentioned to be 50% or 0.5, G is 2.7, so 0.08654, that becomes the water content, that I can use it here. So if we calculate everything after substitution, 19.113 kilonewton per meter cube becomes gamma B here in this 4 meters. Then here anyway we know that it is 20 point something. Okay. Then gamma saturated of clay remains the same. Now if I write the expression at the top of the clay layer, okay, at the top of the layer we have gamma B H1 plus gamma saturated of sand multiplied by H2. Let's say 19.113 is there, into 4 is there, that 4 meters, plus gamma saturated of sand is 20.635 into 1. Yeah, this is the total pressure after pumping, 97.0. Now before pumping, what was the total pressure? It was 103.175. Total pressure was more because of the standing water, right? Now it has reduced to 97.0. Pore water pressure is only for 1 meter, 9.81 into 1, because if you insert a piezometer here, how high the water goes? It goes only up to 1 meter, that's why 9.81 into 1. Sigma dashed phi, that is effective pressure, is total pressure minus pore water pressure, which becomes 87.277 kilopascals. Okay. Now at the bottom, At the bottom, similarly, this 97.087 up to this level is there, plus it is below the water table, that's why 18.15 into 4, that becomes 169.687. U will be 9.81 into 5, only 5 meters. Then sigma dashed V becomes 172.99 minus 49.05, which will give you 120.637. Okay, here what you can observe is I have given the values before pumping. Sigma dashed V 54.175, whereas sigma dashed V is 87.277, means if the water goes, the effective pressure will be more. It is true even in the bottom case, where sigma dash V was 87.475 earlier, and after pumping out it has become 120.637. It has increased, right? So this one observation you can make in this problem. Okay, we'll go to the next one. Okay, other than the problem, there is a concept of quicksand condition and critical hydraulic gradient. That's what we'll discuss and then go further. So here what happens is, again mentally you do an experiment. You got a tube which is attached to a bigger diameter tube. I have poured in water, let us say the water level comes to the same at both the ends. Here we'll put the saturated soil, right? Here we'll put the saturated soil, right? And then we'll have soil. This is perforated plate or plate with holes or porous stone, etc., so that the water will be in contact with the soil but not directly. Maybe membranous material is put in between. Okay, now you add the water little more. What happens is the water will rise even in the soil also. If it is porous, obviously it will rise into the water. Now you increase the water there up to that level, so water will rise up to that level. Increase it little more, what happens is there will be water which is flowing out, because there is an effective head which is above this, right? Above this much, whatever head is there, with that head the water starts flowing out. Then still further if you increase, okay, still further if you increase, what happens is there may be a condition where the particles of soil will be lifted up and drop down. You can just see here the pressure, effective pressure is so much that particles themselves will be lifted up and then again pulled back. So this condition of soil particles getting lifted on the surface and then again dropped down back because of effective pressure is zero, then this phenomenon is referred to as quicksand condition, or it is also called quicksand condition, or it is called sand boiling. Another name used for this is sand boiling. Okay, now technically we'll see what this is or how this is calculated. This phenomenon of sand particles getting lifted up and dropped due to zero effective pressure is known as quicksand condition. So you have to mention that it is a zero effective pressure and sand particles will be lifted and dropped down. Okay, critical hydraulic gradient. The state of stress at point O, I have considered some arbitrary point O situated at a depth h2. You can just see here h2, this is point O. From the top of the soil column may be computed as follows. Vertical stress at O is sigma V0, that is gamma WH1, here there is gamma WH1 plus gamma saturated into H2. If gamma W is the unit weight of the water, then the pore water pressure U0 at O will be equal to h1 plus h2 into plus x, here there is extra, plus x, that will be equal to gamma w. Just see whether it's okay. h1 plus h2 plus x, this is the upward thrust. If gamma saturated and gamma dashed, saturated and submerged unit weights of the soil column respectively, the effective stress at O will be equal to sigma V0 minus U0. Sigma V0 is, you can just see here, H1 gamma W plus H2 into gamma saturated minus the upward thrust because of this pore water pressure, H1 plus H2 plus X into gamma W. If you simplify this, we get effective pressure sigma dashed, which will be simply equal to H2 into bracket gamma saturated minus gamma W. Or, minus, you got X gamma W also, which is equal to H2 into this particular term, gamma saturated minus gamma W is gamma dashed, minus X into gamma W. Okay. Now this is an important condition that we will be putting. Till now it is just effective pressure. All this is effective pressure statement. You know that effective pressure is total pressure minus pore water pressure. Total pressure will be because of H1 gamma W, H2 gamma saturated minus pore water pressure, which is because of the standing water on the other side, is this much, H1 plus H2 plus X into gamma W. If you simplify, we are ending up with an equation H2 gamma dashed minus X gamma W. Right? For quick sand condition, we have said that the effective stress has to become 0. Means this term, whatever you have, should be equated to 0. We get critical hydraulic gradient I critical as, now if you set this equal to 0, that is sigma dashed is equal to 0, which is H2 gamma dashed minus X gamma W, or look at this, what we have is X divided by H2, which will be critical hydraulic gradient, which will be equal to X divided by H2 will be equal to gamma dashed divided by gamma W. That is gamma W dashed is gamma W G minus 1 divided by 1 plus C. This is remaining as it is. This cancels off. You will be left with I critical hydraulic gradient as G minus 1 I critical G minus 1 divided by 1 plus C, where G is the specific gravity of the soil particles and D is the Void's ratio of the soil mass. Therefore, critical hydraulic gradient corresponds to hydraulic gradient which tends to a state of zero effective pressure. Hence, critical hydraulic gradient is given by I critical equal to G minus 1 divided by 1 plus C. Same equation, it is written once again here at the bottom. Okay. Problems on critical hydraulic gradient. It's given the porosity of a certain 1 divided by 1 plus C. Porosity is N equal to 50%, 0.5. Then what else? E can be calculated. E will be equal to N divided by 1 minus N, 0.5 divided by 1 minus 0.5, that is 0.5, equal to 1, right? And similarly, E for dense state, it is only 34%. So in that case, E becomes 0.34 N divided by 1 minus 0.66 whatever amount is there, that will be that. Then specific gravity is 2.7. Estimate the critical hydraulic gradient in loose and fine. So I critical, I have to substitute. In the first case it will be 2.7 minus 1, that is 1.7, divided by 1 plus E. E has become 1. 1 plus 1 is 2. Then critical hydraulic gradient in compact state will be equal to, so again 2.7 minus 1, that 1.7 remains as it is, divided by, I got 1 plus E. This is approximately, let's say 0.5, 0.34 and 0.66. I'll hold it as 0.5 roughly. So this becomes 1.5. Okay, 1.7 by 2, 1.7 by 1.5. So critical hydraulic gradient will be more in compact case, right, and less in loose state. In the sense, in the loose state there is easy possibility that quicksand condition will occur, whereas in compact case it takes more of value of hydraulic gradient so that soil boiling, sand boiling can occur. Okay, fine. Okay, piping effect. What it means here is, I'll explain you. The things that are shown in the figure are, there is an earthen dam with clay or silt, that is impervious blanket, it is like that. And then there is filter, this is filter, here there is a water standing, and then here there will be obviously some quite impervious layer. Now if water has to go on the other side, assuming that this is bit porous, so water will enter, I'll show you here, water enters here and then goes right up to that and then try to go there, right. If the water has entered from there, obviously that also goes and then joins. So like that continuously the water will be flowing in porous media. This is the flow occurs. Now by chance, let us say when the water comes out here, the exit gradient or hydraulic gradient is equal to critical hydraulic gradient. Now what happens is the soil particles here will be getting lifted and dropped. They will be lifted, sooner they lifted they move a bit away and dropped. So there will be a small hole that is created because of displacement of the particles. Now what happens is the water which has to move through the soil will lose the head fine. It will be losing its head. Means what? Suppose there is a standing height of water 10 meters. Gamma H is equal to 9.81 into 10. That much of force, that much of pressure pushes the water through. But as it moves through, it loses the head because of friction. By the time when it comes out, that is called hydraulic gradient. The head that is left and then, okay. Now if that hydraulic gradient is quite high, there is every possibility that it will be moving away. If that is to say, the residual head after moving, if there is a lot of head left, this happens. And once the particles moves, the water has to pass smaller distance. Because of that, it will be left with more of head, and easily it will be able to push out particles there. So this, what happens is the hole on the downstream side now propagates backwards continuously with picking up of soil particles because of the exit gradient. Now this propagation continues and then joins the upstream end. Because of that, the water easily passes through. So if one pipe kind of structure created like that, and then another one is created, now the whole base of the earthen dam becomes porous, on one fine day this settles down. It gets down because it has become all porous. So this effect is known as piping effect. The reason is exit gradient is such that the soil particles will be easily lifted and dropped, or quicksand condition occurs, right? Exit gradient is equal to critical gradient or even less than the critical gradient. Because of that, the particles will be removed and dropped, and back propagation of that hole creates piping. Okay, so piping effects: upward seepage at the toe of the dam. Whatever I have explained, the same thing is there. At the toe of the dam here on the downstream side causes local instability of the soil in that region, leading to erosion. Particles will be picked up and then there will be erosion. A process of gradual erosion and undermining of the dam may begin. This type of failure, known as piping, has been a common cause for total failure of earthen dams. The initiation of piping starts when exit gradient of upward flow is close to critical hydraulic gradient. Factor of safety, that's why, is defined as critical hydraulic gradient minus divided by exit. So this should have been factor of safety. I'm sorry, this one is actually factor of safety against piping, F. It's I critical divided by I exit. Now here I exit is the maximum exit gradient, whereas I critical is the exit critical hydraulic gradient. The maximum exit gradient can be determined from the flow net. I have told you already. A factor of safety equal to 3 to 4 is considered adequate for the safe performance of the structure. Means critical hydraulic gradient should be much more than the exit gradient. Exit gradient has to be less, so that when the particles try to come out, it is not easy for the particles to come out. Okay. Now design of filters. When seepage of water flows from various filter, here I have shown here, this is called filter, so that this one is so designed that particles will not be going out, but water should go out easily. That is the concept of filter design. When seepage of water flows from a soil with relative fine grains into a coarser material, there is a danger that the fine particles of soil may wash away into coarse material. Over a period of time, this process may clog the void spaces in the coarser material. Such a situation can be prevented by the use of protective filter between two soils. Conditions for proper selection of filter material. This is an important factor, and these two conditions are important. One, the size of the voids in the filter material should be small enough to hold the larger particles of the protected material in place. The filter material should have a high permeability to prevent buildup of large seepage pressures or forces and hydrostatic pressures in the filters. The experimental investigation of protective filters provided the following criteria, which are to be followed by or to satisfy the above conditions. Means filter design has to have criteria number 1, that is because of this, criteria number 2 because of this. There is a condition D15 of filter. You know what is D15? D15 is 15% of the particles of soil are lesser than this size, D15 size, right? D85 is 85% of the particles are lesser than this size, D85 size, right? So this is D15 of filter, D85 of that soil, right, which is being protected. It should be less than 4 to 5. D15 of filter and D15 of soil should be greater than or equal to 4 to 5. Okay, with this we'll stop. Thank you.